So, okay, what we are discussing till now, we are discussing about a data structure called binary decision diagram, or in particular we are looking into ROBD, reduced order binary decision diagram. And we have seen that with the help of this data structure, we can represent most of the all Boolean functions, and it always gives a compact representation of our Boolean function. Also in last class, we have introduced how we are going to represent transition system with the help of ROBD. Also we have seen that if we are going to take some set of states, okay, we are having the entire transition system, we are looking for a particular set of states, then this particular set of states can also be represented by ROBDs. So, we can represent the entire state space or entire state transition diagram with the ROBDs, and state of states also can be represented with the help of ROBD. And I have slightly introduced that this particular data structure can be used to implement the model checking algorithm. And when we use ROBDs or in particular OBDs to represent our transition system, and we are going to implement a model checking algorithm, then we call this particular model checking as your symbolic model checking, because we are symbolically representing the entire system. So, basically what happens in our model checking algorithm? What is the basis of our model checking algorithm? If you look back, you will find that it is nothing but some graph traversal algorithm, because the Kripke structure they are using to model our system can be treated as a graph, and in that particular graph we are using some graph traversal algorithm to look for a particular set of states where a given property is true, and the model checking algorithm return this particular set of states. So, in this particular graph traversal algorithm, if you look minutely, you will find that our basic requirement is to find the predecessor state of a given set of states or a given state. Okay. So, this is the basic thing that we need to find out the predecessor state of a given state or the set of states. Okay. So, for that, what happens? We have to somehow find out the predecessor state. So, just like that, if I am going to consider this particular system, okay, so this is your S0, S1, S2, S3, S4, S5, and say that the atomic proportion P is 2 in S3 and S4. Now, if you look into these things, what you call, say, if we are going to find the states where X P is 2, that means in all states, in all part where in the next state P is 2. So, this is X P, in all part next state P is 2. Now, in this particular case, first we are going to see the states where P is 2. So, in this particular case, we will find that the atomic proposition or the CTL formula P is 2 in state your S3, S4. That means, we are going to get this particular 2 state S3 and S4, and we can say that this is a substate X. Now, in our model checking algorithm, what will happen? We are going to find out the predecessor state of these two states, or say this is subset X. Then we are going to get the predecessor as your S1 and S2. Okay. S1 and S2 are the predecessor states of this particular subset X. Now, for here what will happen? We are going to look for pre-there exist X and pre for all X. In last class I have introduced. That means, for all X means all the transition is coming to this particular subset, and pre-there exist means at least one edge is coming to this particular subset X. Now, in this particular A X P, in all part in next state P is 2, that means all the transition must come into this particular subset X. So, in this particular case, now the predecessor state we are getting S1 and S2. Now, we are going to look for this particular criteria whether all transitions are coming to this particular subset or not. We will find that for S1 all the transitions are coming to this particular state subset X, but from S2 one of the transition is not coming into this particular subset X, it is going outside of this particular. So, that means pre for all X will give me this particular state S1. That means, I can say that A x p in all part in next state p is true is in state S 1. So, we are going to get this particular state S 1 and in this particular state S 1 p 1 is true. You just see that in our model checking algorithm our basic requirement is to find a predecessor state only. If similarly, if I am going to look for that A f phi or say E phi 1 until phi 2, in all those cases what will happen? We are going to start from a particular set of states and we are going to traverse this particular graph in backward direction, backward traversal basically, and we are going to collect more and more states and we are going to say that we are going to find out which are the states that A f p or A f phi or E phi 1 until phi 2 is true, and eventually we are going to get a set of states, and our model checking algorithm is going to return this particular set of states. And we have seen that we can use ROBDDs to represent this particular set of states, and ultimately our model checking algorithm or symbolic model checking algorithm is going to return me those particular set of states in symbolically, which will be represented with the help of an ROBDDs. So, this is the basic thing. So, when we are going to use ROBDD for model checking algorithms to get the symbolic model checker, what basically we need these two function pre dear exist x and pre for all x. Okay. In last class we have introduced these two notions and I have explained it. Now, also we have seen one important relationship between pre dear exist x and pre for all x, and we can see that pre for all x can be expressed by this particular expression s minus pre dear exist s minus x. So, this is a relationship between our pre dear exist x and pre for all x, where s, what is s? S is nothing but set of all states, that means we are going to consider all the states of my transition system, and x is a subset of this particular s. That means, we are going to look for what are the predecessor state from this particular subset x, and if we can calculate now pre dear exist x, okay, then from if I know these particular things, then very well always I can calculate pre for all x also by using this particular relationship. Okay. That means, we need one procedure to calculate pre dear exist x. Okay. If we have this particular procedure to evaluate this particular set of states, then very well we can evaluate this one also by using this particular relationship. Now, we are going to see how we are going to evaluate this particular set of state, that means pre dear exist x. Okay. So, we need a method to calculate this one, and this is the basis of our symbolic model checking algorithm. If I give you a set of states, always my requirement is to find out what are the predecessor state, and out of that I am going to see what are the states where it is going to satisfy pre dear exist or it is going to satisfy pre for all. Okay. Now, in this particular case, now how we are going to look into it. So, we are going to look for a procedure for pre dear exist x, where what is the input? The input given to us is your b x, it is the OBDDs for the set of state. Okay. So, we are having a set of states, say this is a set of state x, we are having some states say S 1, S 2, S 3, say something like that. So, B x, we are going to say that this is the BDD representation of this particular subset x. Okay. And secondly, we are going to say that B arrow, basically we are having the transition system and the transition system. Already we have seen or we have discussed how to represent the transition system with OBDDs or maybe ROBDDs. So, we say that B arrow is the OBDD representation of our transition system. So, basically we are getting two BDDs, one is your Bx, this is the OBDD representation of our set of state x, and B arrow is the OBDD representation of our transition system. Now, one basic requirement is there for this Bx and B arrow. What is that basic requirement? Already I have mentioned that since we are going to use some operation on these two particular BDDs, so they must have computable variable ordering. Already we have mentioned what is computable variable ordering. they must have same variable ordering. Okay. So, we are taking two BDDs or OBDDs as our input, and both the OBDDs must have computable variable ordering. Now, what is the procedure? What we are going to do? So, this is very simple one, I am going to explain it. As per procedure, we are going to say that rename the variables in Bx to their prime versions, and we call this resulting OBDDs as Bx prime. What is prime version of a variable? Because already we have seen that if we are going to represent a transition system, we need two set of variables to represent those particular transitions. Say if I am having a transition from say SP to say Sn. SP is my present state or current state, and Xn is the next state of this particular transition say T1. So, this transition will be represented by the order pair of two states. So, basically this state current state will be represented by some state variables. Say if we need n state variable, then we are going to take the help of n state variables say from x1 to xn. To represent this particular Sn, we need another set of variables, and this set of variables are basically the prime version of this particular original variables. Now, what we are going to do? We are going to rename those variables in Bx to their prime version. I will explain it what we are going to get. Then we are going to compute an OBDD for this particular operation. Okay. First, we will use this particular apply algorithm with this particular dot operator with this two BDDs, OBDDs for transition system and OBDDs for the set of states where the variables are renamed to their prime version, and this particular apply algorithm will give me an OBDDs. Okay, and where the variable ordering is same with your B arrow and Bx prime. Now, after that what we are going to do? We are going to apply this particular exist algorithm where we are going to make it independent of this particular prime version of those particular variables. So, x, but basically it is a vector. I can say that what is your x set? X set is nothing but the vector of all the variables that we are using x1, x2 to xn. Similarly, x prime hat is the vector of variable of prime version of this one x1 prime, x2 prime, like that xn prime. Okay. So, these are the two steps that we have to apply, one renaming of the variable, and second we are going to use this particular method. First using the apply algorithm with dot operator, then we are going to use the exist algorithm. Okay. So, these are the two steps that we have to perform when we are going to get this particular pre-dir exist x. Okay. Now, rename the variable in Bx to their primed version. Now, what happens if I am going to give you a function say f is equal to ab plus a prime ab plus a dash c dash. Now, if I am going to write another function, say I am going to say this is your f1, and I am going to say write another function say f2, I am going to say that x y plus x prime z prime, okay, or x bar z bar. I can say that this is bar is basically negation of that thing. So, I am saying that x bar z. Now, if you look into this particular two function f1 and f2, now I can realize, or you can realize that these are equivalent function, because what will happen, the variable a is correspond to variable x, variable b is correspond to variable y, and variable c is correspond to variable z. That means, they are having the name of the variable is different. That means, you can say that we are just renaming this particular variable from a, b, c to x, y, z. If you look into the evaluation, if any evaluation say if x equal to 1, a equal to 1, b equal to 1 and c equal to 1, whatever functional value we are going to get for f1 with x equal to 1, y equal to 1 and z equal to 1, we are going to get the same evaluation for f2. For all combination, we are going to get the same evaluation. So, that is why we are going to say that f1 and f2 are equivalent, or they are representing the same function. So, these two functions f1 and f2 are basically same, they do not have any difference, only we are renaming the variable a, b, c to x, y, z. Now, similarly, in our transition system also, now what will happen? So, for F1 I am going to get an BDD. Okay. So, this is your F1. If you look for the BDDs for F2, we are going to get the same BDD. There will be no difference because they are representing the same one. Only the variables will be renamed now. If this is your A, now it will be renamed to X. Similarly, if next level, if I am having the variable B, then there it will be Y only. Now, similarly, what will happen in our Bx? This is the OBDD representation of our set of state X with this particular variable X, Y, Z, X1, X2, X2. So, Bx is a your distinct BDD representation of a subset of states, and say the variables are your x1, x2, x3 like that xn. Now, Bx prime, what we are having? We are going to have the same BDDs, but we are renaming this particular variable x1 prime, x2 prime, x3 prime, xn prime. Okay. So, this is the scenario that we are having. Now, I will see this thing, say if I am having a transition system something like that. Say this is the subset X, the set I am having say X4, S5, S6. Now, what basically happens? We are having, if I am having a transition Sn to Sm, then we are going to represent this transition with this particular order pair Sn Sm. Okay. Now, when I am having this particular subset, so I am just saying that this is the Bx is representing the this particular subset S4, S5 and S6. Okay. Now, say Bx they are representing with a state variable. Now, I am just renaming those particular variable in Bx prime to their prime version x1 prime, x2 prime, something xn prime. Now, what is the basic aim? Basically, if we look into those particular transition, because our aim is to find out the predecessor state. That means, these are basically next state variable and we are going to find out what are the present state variable. That is why we are renaming this particular variable to their prime version, just to capture those particular transition. Okay. So, this is our basic aim. So, after renaming the variables, we are getting the same structure as OBDDs. So, whatever OBDDs we have, the structure will remain same, only we are renaming those particular variable. So, after renaming the variable, we are getting Bx prime. Now, what is the next step? Compute OBDDs for exist x prime hat, I should say, apply dot B arrow Bx prime using the apply and exist algorithm. Now, in this particular case, what happens? You just see that. If I will consider this particular relations, a simple transition system, so that I can, for the sake of completion, I will complete it. So, this is a subset X. Now, we are getting B arrow as the OBDD representation of my transition system, and Bx prime is the I will say that representation of this subset X. Now, we are having this representing this particular subset with the prime version of the variable. Now, in B transition, the BDD of the transition system, we are having all the variable x1 to xn and x1 prime to x n prime. All the variables are available in your b prime, and your b x prime we are having the prime version of the variable. Okay. Now, when I use this particular apply operation, the dot operation, what basically dot, it is going to give me the intersection of two sets. Basically, already we have discussed, we have mentioned that this, if you apply this particular dot operation, it is going to give me the intersection of two states. Now, I am using two BDD, this is one is representing some states and second one is representing the anti-tangent system. Now, when we apply this particular dot operation, it is going to give me a common or intersection of these two particular states. Then basically, what we are going to get after applying this particular dot operation, we are going to get basically those transitions. Say this is T1, T2, T3, T4, T5. So, it is going to give me in my entire BDD representation of the entire transition system B arrow, I have all the transition. Now, I have just intersect this particular transition, all transition with this particular subset. Now, whatever we are getting the transition that are all coming into this particular X, since other transition will simply go away. So, this is a intersection operation we are doing. So, basically we are getting, after performing this particular apply operation, after apply, what we are getting? We are getting those particular transition only T1, T2, T3, T4, T5. Okay. We are getting these 5 transition, because these are the 5 transition, these are the intersection of these two particular sets. Now, when whatever is the result we are getting over here, we are getting the transition that is coming into all the transition coming into this particular subset X. Okay. Now, in this particular BDD, whatever resultant BDD we are getting, say I am going to say that this is your BDD, say only transition that it is having. So, this particular BDD is having all the variable x 1, x 2 to x n and their prime version x 1 prime, x 2 prime, x n prime. So, we are getting those particular transitions which are coming into this particular set X, and this particular transition will be represented by this all those particular variables, the state variables along with your next state variable. Now, whatever BDD we are getting, now what we are doing it, now we are using this particular exist algorithm, and what we are making B exist x prime hat. That means, we are taking this particular vector x prime hat, x 1 prime, x 2 prime, like that x n prime. So, what we are doing basically, whatever resultant BDD we are getting, we are making it independent of this particular prime version of the variables. You just see what we are doing. We are first doing the apply operation, and we are applying this particular dot operation, we are getting the intersection, we are getting those particular transition which are of our interest. That means, the transition which are coming to this particular set X. Now, from that what happens, now we are making it independent of the next state variable. So, when we are making it independent of this particular next state variable, so what happens, now these transitions are having all the variables x 1 to x n and their prime version x 1 bar to x n bar. So, this is basically representation of this particular, say from present state to next state all those order. Now, we are making it independent of those particular next state variables. So, it is having all the variables. Now, we are making it independent of next state variable. So, in this particular case, what we are getting in the resultant BDD, whatever final BDD we are getting, now it is independent of next state variables. So, eventually we are getting the representation of those particular states only. Just try to visualize it and try to understand it, that we are getting these particular states only. They are representing those particular states, and these are represented by the state variable, present state variable. You will just see that whatever the ROBDD or OBDD returned by this particular operation, it is going to give us the states or OBD representation of a substate from where all the transitions are coming into this particular subset X. Okay. So, this is the way we are evaluating. So, that means we are getting a resultant BDD from that resultant BDD of a subset, and from those particular all the state from this particular subset, all transitions are coming into this particular subset X. So, this is the way we are calculating the all the predecessor state. So, if all the predecessor state we are getting in, so predecessor there exists X will also be the same state, because we are getting all the states from where the transition all the transitions are coming into this particular subset X. So, that means at least there will be one transition which is coming into this particular state. So, it is going to give me the there exists X. So, if I am having some more transition something like that, still these two states will come into as a resultant state. Now, since at least some of the states are coming into this particular X, that means this is also candidate for your there exists X. So, with the help of this simple operation, with this particular two steps, first we are renaming the variables of Bx, and then we are applying this particular operation or using this apply operation and exist operation to get the predecessor state, and whatever predecessor state we are getting, all those states will give us the there exists X. And once we are having that there exists, we can very well calculate the for all X. Already we have seen this is nothing but S minus there exists S minus X. So, now we are having a method to find out there exists X, and once we can calculate there exists X, we can calculate for all X also. Okay. Now, this is the basis or this is the basic requirement of our symbolic model checking algorithm. Okay. Now, in this particular case, now we are going to see how we are going to implement those particular symbolic model checking algorithm. Already we have seen that we have discussed with 4 temporal operator, next state, future, global and until, and these 4 temporal operators are always preceded by the part quantifier A and E, that means in all part and there existed part. So, we are getting 8 different combination, but already we have seen that if we get 3 operators also, that will going to give me a complete set of operators. So, in that particular complete set of operator, I need the next state operator, I need the until operator, or I need either future or global, any one of these two. So, either all A or EX, whatever it may be. So, we need 3 operators, and already we have discussed the algorithm for those particular 3 operators, that complete set of operators. Now, we are going to see how we are going to implement those things symbolically. That means, how we are going to implement symbolic model checking algorithm. So, first operator is we are talking about EXP, that means there exists a part where next state P is true. This is the simple procedure. What we are talking, first we are going to take all the states where P is true. So, satisfactorily P is going to return me all the states where P is true. So, we are going to collect those states in such a way that from those particular states we are having a transition to S1 such that S1 belongs to this particular set X. Okay. So, this is basically the evaluation of EX. Now, this procedure we can implement symbolically. So, how my symbolic model checking algorithm should look like? You just see that EX B5. What is B5? It is OBDD representation of the state of states where phi is true, because when we are going to evaluate EX phi, we must know the set of state where phi is true. Okay. We know the set of state where phi is true, and we are going to represent those particular state of state with the help of an BDD, and we are going to say that B phi is the BDD representation of those particular set of states where phi is true. So, this is analogous to X, we are assigning that set of phi where the set of states where phi is true to this particular X. So, this is basically analogous to X is equal to set of P. Okay. Now, what happens, and B arrow is the OBDD representation of our state transition system. Now, whatever variable we are ordering we are having for B arrow, that same variable ordering we should maintain for B phi also. Now, from that what will happen, simply you evaluate there exists B phi. Now, we are getting all the sets, this is analogous to this particular thing y is equal to, we are going to collect all the set from S, so that we are having a transition from S to S dash, where S dash belongs to this particular x. So, this is the way that we are going to have. So, we simply use this particular pre-DRexist x. Okay. Now, what basically says, see that you can think about something like that. Let's say if P is true over here, then first we are going to get B arrow, which is the representation of this particular whole transition system. Then we are going to get say B phi, the state of state where phi is true, say these are the two states where phi is true. So, I am going to say that SM and SN. So, this is B phi is nothing but a BDD representation of your SN and SM. Now, we are going to look for the all predecessor state. So, if you going to calculate the predecessor, basically these two states will come, okay, as per our this evaluation, return pre-DRX is B phi, and these are the states where EX phi is true. Okay. So, we are going to give the input as of B phi and B transition, and from that we are going to evaluate this particular predecessor state. Just see that pre-DRexist x or pre-DRexist B phi is going to give me the set of state where EX phi is true. Okay. So, this is one algorithm, this is a very simple one. Now, second one we are going to say that set AFP. So, determine a set of state where AFP is true. Already we have discussed this algorithm. So, we are going to perform this operation wherever P is true, we are going to say that AFP is true. This is as per the semantics that we have discussed. Our semantics says that present state includes the future behavior, and after that we are going to look for all the states from where we are having a transition to those particular states. So, we are going to collect all states, so that we are having as this sum having a transition from S to S prime, where S prime belongs to Y. Okay. So, this is basically what happens. You can see something like that. AF phi in all part in future phi may be true. So, if I am having something like that, then say if P is true over here, just say that in one state I am going to take, then or say P is true over here also, then I am going to take this particular subset. We are going to calculate the previous state, since all the transition data coming from this. So, these two states will be marked with your AFP, AFP. Now, we are going to perform the backward traversal algorithm. So, in this particular case, all the transition are coming to this particular subset X. So, AFP will be true over here, AFP will be true over here. Then if I am going to look for this one, then AFP is true for two states, but this state is not, AFP is not true. So, this state will not include. So, we are going to repeat this particular procedure. So, that is why we are saying that collect some more states, then again see go over here and see where x is equal to y or not at some point of time. That means, we are not adding any more states, then we are going to terminate this particular procedure. So, this is the same procedure we can use now, we can apply our symbolic model checking algorithm. So, what we are having said, B phi is the OBDD representation of the set of state where phi is true. First, we are going to start from those particular set of state where the given formula is true. Like that, we are starting from this particular subset and now going to perform the predecessor operator and going to find out what are the states where AFP is true or F phi will be true. So, first we are going to take the OBDD representation of the set of state where phi is true, and B arrow is the OBDD representation of our entire transition system, or you can say that it is OBDD or it may be a reduced OBDD also. So, we are starting with these two OBDD B phi and B arrow. Then we are going to take one particular these things B x, basically it says that these are all states of the system. I am just representing it with the help of this BDD. So, we are going to take one BDD where it is going to represent the entire states. It is not a state transition system, but this is the all the states OBDD representation of all the states. So, this is basically analogous to I am saying that initially taking that x is equal to your S entire state space. Now, we are going to repeat this particular procedure the way we are doing in the previous case, that repeat until x is equal to y. So, we are going to repeat this thing until that B x is equal to B y B phi. So, B phi is assigning to B x, that means we are keeping the previous information. Now, we are going to use this particular operation. We are going to use this particular apply plus, because what we have to do, whatever we are having, we are going to perform the union with some new mode states. Okay. Now, what are the new states is coming? So, this is basically union. Union is going to use by this particular plus operator. Add B phi is the set of state which correspond to this particular y state of state where phi is true. And now, this is your A f in all part in future. So, that means we need P for all. So, this is basically we are going to calculate P for all B phi, and how to calculate it? Already we have seen that we are having procedure to evaluate P, there exists B phi or x. So, we will use this particular relationship to get P for all x. So, that is why I am just scriptly I am writing over here, I am not writing the entire expression. So, we are going to look for all the predecessor state from where all the transitions are coming into this particular subset where phi is true. Okay. So, I am getting a new set, then again I will go back and repeat. Now, I am going to see what is the previous set of state we have. Now, whether it is equal to B phi or not, the new B phi. If they are equal, then we will terminate. If it is not equal, that means you have added some new mode states. Like this particular case, we have added some new mode states. Now, we have to check again the predecessor of those particular new states. So, we will again enter to this particular procedure. Look. So, see that this is a simple conversion of our model checking algorithm to the symbolic model checking algorithm, where we are using OBDDs, ordered binary decision diagram, to represent the entire system and represent the set of states where a particular formula is true and applying this particular algorithm. Now, similarly, we need one more procedure where we are having set E u p until q. So, here exists a part p remains true until q becomes true. So, E p until q. So, what is the procedure? Already we have discussed it. So, what we have to do? We have to look for p remains true until q is true. So, this is the expression or this is the evaluation that we did actually. What is the W? W is the state of state where p is true, that means we have to collect those particular states and intersection with this particular new state, that we are having a transition from those particular state and p must be true. So, basically you just see the transition, just I am drawing it something like that. So, if we are having this thing, then what will happen? First, we are going to look for those particular states where we are looking for E p until q. So, we are going to look for those particular states where q is true. Okay. Since q is true over here, so I can say that E p until q is true, because it is as per our semantics that presence into the future. Now, from this particular state, what happens? We are going to look for the predecessor state. So, we are going to get this particular 3 predecessor state. So, in this particular case, p must be true and in next state E p until q must be true. So, this is the scenario that we are having. W, it is where the set of state where p is true, intersection with those particular states where in next state q is true. So, in this particular case what will happen, in this state whatever we are getting over here, then you will find that this particular state p is true and next that E p until q is true. So, we can say that E p until q is true. Here also you will get that E p until q is true, but in this particular state E p until q is not true because p is not true over here. Now, I am getting some more states. So, we are going to look for the predecessor of those particular new states. So, I am going to get these two states again with the same property, same constraint that p must be true over here, say w intersection of those particular things. We must have a transition to this some state of this particular state y, where y is the new set we are constructing. So, again you will find that E p until q will be true over here, but it will not true at that particular point. Okay. Now, when we will come back to these things again E p until q will be true. So, this is the way that we are evaluating E p until q. Now, this same procedure we are going to implement symbolically. Now, what we have to see again similar to the previous one. Now, it is basically E psi 1 until psi 2. So, we need two BDDs to represent the state of state where psi 1 and psi 2 are true. So, we are using starting with these two BDD B psi 1 and B psi 2. B psi 1 is the OBD representation of the set of state where psi 1 is true and B psi 2 is the OBD representation of the state of state where psi 2 is true. So, these are the two things we are getting. Then we are taking the entire state transition system B arrow, this is the OPDD representation of the entire transition system. Now, as per our semantics, wherever psi 2 is true, then E psi 1 until psi 2 is also true on those particular states. So, I am starting with this particular psi 2 and we are saying that initially making B x is equal to psi 2. So, initially I can construct B x as the entire states all the states of my state space. So, initially wherever psi 2 is true, E psi 1 until psi 2 will be true. So, we are just keeping this particular assignment. So, now we are going to compare these things, we are going to repeat this particular loop. Now, storing all those particular states I B psi 2 to B x, just renaming it. Then we are again using this particular expression. So, what happens? This particular portion will give me this portion. So, pre there exists x, it is giving me all the predecessor state. In predecessor state psi 1 must be true. So, we are doing this particular dot operation, that is the intersection, that means this is the state of state, all predecessor state. Okay. Now, B psi 1 is the state of state where psi 1 is true, that means this is nothing but the state space representation of this particular W. W is the set of state where psi 1 is true. So, we are taking the intersection, that means it is going to give me those particular two states in my previous example. So, it is returning my these three previous predecessor state, but after doing the intersection I am going to get these two states only. So, this is the operation we are performing. So, these are the states where it is true, and now I am going to use this apply plus, that means I am going to do the union operation. That means, first we are collecting the state of state where psi 2 is true and we will say that psi 1 until psi 2 will be true on those particular state. Now, we are collecting new more states. So, we are going to use the union operation, we are adding them to this particular state. So, that means, this union operation has been performed by this particular apply plus operation. Okay. So, now we are adding some more states where this particular E psi 1 until psi 2 is true, like that. We are adding these two states. Now, we will again repeat this particular procedure to get this state and this state. Okay. So, this is the way that we are doing. So, after adding this particular two states, we will go into this particular loop. Again, we are going to check whatever is the new states we are getting, whether it is equal to our previously collected state or not. Okay. If they are equal, then we will terminate. If they are not equal, then again I am going to do this same procedure. Okay. This is similar to repeating these particular steps. Okay. So, in this way we are calculating it. So, you just see that all these three operators, what are the operators that we are talking about? Here three operators we are talking about. One is your so we are talking about three operator EX phi, AF phi and E phi 1 until phi 2. So, since we are having the procedure to evaluate these three operators, now we can evaluate the other operators also, because we have seen that these are the complete set of operators. Okay. So, we need basically 8 operators, temporal operators that we have discussed till now. We are having 4 temporal operators, next state, future, globally, until, and with respect to this particular 4 temporal operators, we are going to get 8 CTL operators with path quantifier A and B in all path and near existing path. That means, AX, AF, AG, EU and similarly EX, EF, EG and sorry, this is AU and EU. So, out of that, if we are having this three procedure for these three operators, others can be evaluated. So, you just see that we are using ROBDDs to evaluate these three procedures. Okay. Now, we are getting a symbolic model checking algorithm, and what is the advantage we are getting? We are representing the OBD, the center state space with help of ROBDDs, and in most of the cases we have found that we are going to always get a compact representation. Again, I would like to mention that the size of ROBDDs depends on the ordering of the variable, but to get the exact ordering is a hard problem. Already I have mentioned all those issues. Okay. Now, we have seen that we have got that model checking algorithm or symbolic model checking algorithm for our testing. So, we use ROBDDs to implement model checking algorithm, and whatever model checking algorithm we are getting, we say this is your symbolic model checking. Okay. We have seen these particular things. Okay. Now, you just see that now we are having enough idea about our model checking, how what we can do with the help of model checker, what cannot be done, all those things we have studied. Now, in this particular class, I would like to mention some tools. Okay. One of the tools is your CUDD. This is basically a package for your decision diagram or say binary decision diagram. So, this is a package for your BDDs. This is CUBD. It is developed in University of Colorado at Boulder. Okay. So, University of Colorado at Boulder, they have developed this particular package. This is a freeware everywhere. For academic purpose, anybody can use it. Now, what you can do? You can download this particular CUD package from University of Boulder, University of Colorado at Boulder, and use this particular package to construct BDD, to manipulate the BDDs. Use it is having all the required algorithm. Another tools I am going to just mention over here, which is your new SMV. This is your symbolic model verifier. It is the extension of SMV, symbolic model verifier, which is the first model checker based on your BDDs. It was developed by Ken Macmillan, who was a student of your Edmund Clark, who is the pioneer of this particular model checking procedure. During his tenure in CMU, he developed this particular SMV. Now, it is having some modification, extension and released as your new SMV. So, this is a symbolic model verifier, where they are using the BDD to represent the entire system and do this. So, with the help of these things, we can model our system or we can look for the property verification. It handles fairness also. Another one I can just mention over here, it is SPIN. This is a tool developed at your Bell Labs. This is initially the LTL model checker. So, we can already we have mentioned about what is LTL, which is so we are having an LTL model checker also. Now, what you can do, you just try to download these 3 packages and try to work with this thing. So, working is also very simple. What you need to do, you have to see, you have to look into the syntax, how we are going to give the input to this particular tool. So, you have to know the syntax of new assembly, how to provide the input, and you have to know the input syntax for the spin verifier. They are using a particular language called Pramela. So, that you need to know the syntax of this particular Pramela language to give the model of your system, and after that, after specifying the property, it is going to check whether the property is true or not. Okay. So, this is the way that we are doing it. So, what happens now, you just try to I am just giving this information. If you are interested, you can download those packages and try to work with those packages. Okay, now, what we have seen in this particular case, this is basically we are discussing about your system design verification. So, we are having a design, and we after coming up with a design, we are trying to verify or check whether my desired properties are true in this particular design or not. So, in this particular case, what we have discussed or what we need, basically we have to come up with some model of the systems. If I am going to design something, say simple one, I can talk about that you are going to design for your traffic light controller. We have to come up with a model, and this model basically we are representing with the help of Kripke structure, which is a kind of your FSM, finite state machine. After that, we have to give our specification or the property that must be satisfied by my model. And here in this particular course, we have discussed one specification language, which is called CTL, computational tree logic. Okay, we have discussed with this particular CTL, we can give the specification with the help of this particular CTL language, and after that we need the verification method by which we are going to check whether the given specification is true in the model that we have given or not. So, for that we have used this particular model checker, or we are using this model checking algorithm. Now, after that, when we look into the model checking algorithm, what we have find or we have observed that we are going to get a polynomial algorithm for model checking algorithm. So, this is the beauty of your model checking algorithm. If I talk about a model checking algorithm, particularly I should say that in particular I will say that this is your CTL model checker. Okay. For CTL model checker, we are getting a polynomial time algorithm. So, which can be manageable, which can be handled, and the method can be easily automated. Now, since we are having an algorithm, which is a polynomial time algorithm, so it can be automated. That means we can have an automated tool, and already I mentioned about some tools like MuSMB, spin like that. And another advantage of this particular model checker is it provides counter example. So, if I am giving a model and I am giving a specification or property, now using this particular model checker, then what will happen if the property is true, it is going to say that yes, this property is true in your model, you can proceed. But if the property is not true, it will give me a counter example, it will give me an execution trace, and it will say that if you follow this particular execution trace, then your given property is false. So, this is some sort of feedback mechanism, it is giving some feedback to the designer team. Now, designer team can concentrate on those particular execution trace and they can fix the bug. Okay. So, this is the advantage about this particular model checking algorithm. Now, what we have seen? We have seen that we are having some problem with this model checker. What is the problem? The problem is state space explosion problem. Already I have mentioned that the state space of the system of the model that we are going to get is exponential with respect to the number of state variables that we have. Already I have mentioned that if I am having a n state variable, the number of possible states will be 2 to the power n. If n is increased by 1, then it will be 2 to the power n plus 1, which will be exponential in nature. How to contain, how to restrict this particular state space explosion problem, or how we are going to work with a bigger system. So, for that we have seen how compactly it can be represented, that transition system can be represented, and how it can be represented what we need. And we have seen that the data structure BDD can be used, or in particular ordered BDD can be used to represent the state space diagram, and most of the time we are going to get a compact representation for those particular state space. So, by using OBDDs, we are coming up with another model checker, and we call this is your symbolic model checker. Okay. So, in case of symbolic model checker, we are using OBDDs to represent our state space, and we are somehow contenting the state space explosion problem. We are restricting the explosion with respect to this particular state space. So, these are the things that we have discussed in this particular part. Okay. Now, as a question, what I am going to say that already if you look back our lectures, then what happens? We have seen how to design an elevator controller. Okay. We have seen or we have discussed a simplified model of our microwave controller. Okay. So, these two we have discussed in our course of our lecture. Now, what we can do now, since you have the model, you know what are the properties that you need to verify. Already I have mentioned something. Along with that very simplified one or very simple one that we have discussed about your mutual exclusion problem for our shared resources. So, these are the things that we have discussed in our course of lectures. Now, what you can do that I have mentioned about some tools like your new SMV or spin. Now, you try to model this system on those particular tools. Model this system means what happens? Already I have or we have discussed about the model. Now, you just try to convert this particular model to the input language of your spin or new SMV, and you see how we are going to write the specification for those particular true and check those particular properties. Okay, just as an example, as a question I am giving you, you download those particular tools, install in your machine and try to check how those particular model checkers are going to work. Now, I am giving some of the problems also. So, what I am talking about that traffic light controller. So, already many a time I have discussed or I have mentioned about this particular thing. Now, you take some complicated system, complicated road network and try to design a controller for this particular traffic on this particular junction. So, that means you need a controller. So, you try to come up with a design, come up with a model and come up with the properties that need to be satisfied this particular controller. Another system you can talk about your ATM. Nowadays, most of you people are using that ATM, automatic teller machine. So, how it is going to work? You must know, and if you try to analyze it, you will find that you will come up with a basic model. So, you try to come up with a model of this particular ATM system also, and after that, after coming up this particular ATM model, then you try to find out what are the properties that need to be satisfied this particular model, and now use those particular model checker to check those particular properties. So, that is why I am saying that use the tools new SMB or spin, because these are freely available for academic purpose. Now, you can come or you can look for the designing or modeling of those particular system and see, try to prove the properties on those particular system. In that particular case, what happens? You will be knowing how to use this particular tools also. Now, what we are looking into it, this is some sort of your designing of our digital system. In this particular course, we are talking about design verification test of your VLSI system. Already I have mentioned or we have mentioned that basically if you look into the design cycle, we have found, you will find this particular step. First, you have to come up with the specification of the system, then we have to come up with a design. Once we have come up with a design, before proceeding further, we have to say that our design is going to work correctly. So, for that we have been coming up with this particular verification methodologies. We are going to check the properties in our model. Once we are coming with this particular, once we verified these properties and we are satisfied that yes, my system is going to work correctly, then we will go for implementation. After implementation, then what we have to do? We will go for this particular testing, whether my implemented circuits are correct or not. Basically, it is going to find out the fabrication fault, and next steps are your next stages are your installation and marketing, and after that you have to maintain it or you have to go for the upgradation. So, these are the design cycle steps that we have seen or we have discussed, that these are the steps when we required when we go for the design of a digital system. And in this particular course, this is about the digital VLSI design. If you see that in this course, we are talking about the design of a digital system, and if you look into it, we will find that we are having three parts of this particular course. One is the design issues, second is the verification issues, and third one is the testing or testing of our design or testing about VLSI design. So, in this course we are having these three issues. In the first module of this particular course, we have discussed about the design issues, how we will proceed to design a system. So, this is the first part of this particular course, and second part we are talking about the verification. So, this is the second part that we are discussing till now. In this particular part, we are talking about the verification issues. So, what we are doing over here, we are coming up with the design. So, while we go for this particular design, we are coming up with a design, we are getting a model. After getting the model, we know what are the properties it must satisfy. So, we will come up the specification and we will apply some verification methodologies to check whether these properties are true or not. So, in this particular part, we are discussing about this particular verification issues, okay, how we are going to go for verification and what we are going to do and all those issues, and we have discussed. And in this particular part, we have just introduced one particular technique called model checking. We have seen how we are going to use this particular model checker, what are the problems, and we have introduced about your symbolic model checker also. And the third part of this course is your testing. So, in next part we are going to talk about this particular testing. One, my fabrication is over, now how we are going to test the system, that before releasing into the market we will say that this is fault free. Basically, in testing, what we are going to do? We are going to find out the fault, and we are going to release a fault free circuit to the market. So, this is basically post implementation or post fabrication. So, next class onward, we are going to talk about the testing of our VLSI system. Okay. That is all. Thank you.